Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to the GitHub page at this given link. In last few lectures, we were discussing the linear discriminant functions where we have discussed the two category case, multi-category case, and also we have discussed the generalized linear discriminant function. So in this lecture, we are going to discuss the linearly separable case for two category classifier. So here our objective is to classify the data samples in the feature space using decision boundary. That means the features are to be linearly separable. Then we have to find parameters of the linear discriminant function. So here we are going to discuss two category linearly separable case. Okay, so suppose y1, y2 and yn, these are n number of data samples from class 1 and class 2. Okay, so we have total n number of samples. So please note down here that these data samples are basically the augmented feature. And how we obtain the augmented feature? So if we have the feature vector x having the feature component x1, x2 and xd, then we obtain the augmented feature y as okay, where this one is just because of the bias term. So here we are going to define our objective in case of two category linearly separable case. So use y1, y2, yn to determine the weights A in a discriminant function gx equal to A transpose y. Okay, so if such A exists, that means if such A exists that A transpose y is greater than 0 for all data samples belong to class 1 and A transpose y is less than equal to 0 for all data samples belongs to class 2. Okay, so then we can say that y1, y2 and yn are linearly separable. Okay, and we always try to find such a vector A that all the training samples are classified correctly. So if it will be linearly separable and all the samples from class 1 will be classified as class 1 and all the samples from class 2 will be classified as class 2, then we can say that samples are linearly classified using this weight vector. So using this discriminant function that we are going to define. Okay. So the question comes, how we can find such a weight vector A. So how we can find such weight vector A. Okay. So let us try to understand this feature space. So here this feature and this feature belongs to class 1 and these two features belongs to class 2. Okay, and this is the decision boundary which separates these feature vectors belongs to two different class. So this is basically A transpose y equal to 0, and perpendicular vector to this separating plane is basically the A vector. So here this is the decision boundary. So this side it will be A transpose y is greater than 0, and this side of the separating plane will be A transpose y less than 0, where A is our weight vector w0, w1, w2 and wd. Okay, now we can normalize the data samples y1, y2 and yn. And what is the normalization here? We have to replace all yi labeled omega 2 by their negatives. Okay, that means yi will be replaced with minus yi. Okay, and only those data samples which belongs to class omega 2. Okay, so what will happen when we normalize the data sample from class 2? So whatever the sample was here, now it is moved to here. Okay, because we are just negating the values of the data sample belongs to class omega 2. Okay, but still we have the same separating plane, but now the decision rule will change something like A transpose y is greater than 0 for all data samples. So now it is not depending on any class labels anymore. That means it is not depending on the class labels. So only this rule is sufficient to classify all the data samples correctly in the feature space. So after normalization, we can forget about labels of training samples. Okay, that means A transpose yi is greater than 0 for all yi. Now we are not considering any class label. So such weight vector A is called the solution vector, because we are looking for this vector. But now the question comes in mind, is this solution vector is unique? Try to understand here that as we have the data samples in the feature space from two different class, then we have this decision boundary, and perpendicular to this is the solution vector, that is A. So if this is a single boundary which will separate these data points from the different class? No, we can have the other decision boundary which will pass in this way. Then we will have the solution vector something like this. We may have the decision boundary something like this. In this case, we will have the solution vector. So that means we don't have a unique solution vector, and this vector, it may lies in a region. Okay, we can define certain region that the vector will lie in this region. So our observation is solution vector is not unique. Okay, so here whatever the region that we have created, so that means here we have many solution vectors. So we can say that a set of solution vector is possible in the d-dimensional feature space, and this space is called the solution region. Okay, the region where our solution vector lies. More formally, solution region is defined as a set of all weight vector which will satisfy A transpose yi greater than 0 for all I from 1 to n. Okay, that means this is set of all possible solution. Here also possible to put some margin on the solution vector. Okay, now let us analyze this figure. Here we have samples from two different class and we have the separating plane. We can have the other separating plane as well, something like this or this. So here we have infinite number of separating planes in this region, but we have two extreme surface that is very close to the boundary of the two class, something like this, and this was the perpendicular vector on this separating plane, and this was the perpendicular vector on this separating plane. So we have defined this region as the solution region. But we can put the margin. So suppose we are considering this amount of margin, and this margin can be considered as the safety margin. Okay, so that after training there will be some margin of safety for the test sample, because whatever the decision boundary we are trying to obtain, that will be good for training samples, but it is not necessary that it will be good for testing as well, because the testing samples are the unknown sample, it is unseen data samples. So if we put some margin of safety so that it may work on the test set data sample as well. So that is our objective, to consider the margin. Okay, so suppose in this case we are considering this amount of safety, then we will have a decision boundary something like this, because we have the B amount of safety, the margin that we have considered. So this side also, if we consider B, okay, so our decision boundary will be something like this. Okay, so then if we will take the perpendicular vector on these decision boundaries, then our solution vector will be something like this, and for this our solution vector will be something like this. Okay, then we will have the solution region with margin of safety. Okay, so we can define A transpose yi is greater than equal to B for all I equal to 1 to n, where B is positive constant and it is called the margin. Okay, but for our further discussion we will consider that B equal to 0. That means our focus will be on the zero margin case. Okay, so we are looking for weight vector A such that A transpose y is greater than equal to 0. So what we can do? So here we will define a criteria function, and that is minimized if the weight vector A is our solution. So we can define our criteria function JA, and we want to minimize this with respect to A. So this is the criteria function that we have defined and we are trying to minimize it. So this type of problem can be solved by gradient descent algorithm. Okay, now try to understand that what is the gradient descent algorithm. So this idea is very simple to understand. So what is the idea? So first we will understand the idea, then we will see the exact algorithm. So idea is that first initialize the weight vector. So start with A1. Okay, then generate next iteration weight vector A2 by taking a small step in the direction of negative gradient of criteria function. Okay, and repeat step 2 until we get the solution. So here the idea is very simple, that first we initialize with some random weight, and then we generate the next iteration weight vector by making a small change in the direction of the negative gradient of criteria function, and this step will repeat it until we will get the solution. Okay, but how this weight vector will be updated? So here, so what is our gradient descent algorithm? We initialize A1 threshold theta, learning rate, that is called eta, and set k equal to 0. In the next step, we update the value of k by k plus 1. In the third step, we update the weight vector in the direction of negative gradient of criteria function. So a k plus 1 equal to a k minus eta k del j a k okay. And fourth step, we will check the condition if mod of eta k grad j a k is less than theta, then we will stop and the updated weight vector will be returned. Okay, otherwise go to step 2. Okay, so this is our a basic gradient descent algorithm. So you can notice here that, so this is the gradient that we are computing in each iteration at the particular given weight vector, and we are multiplying it with a learning parameter which is called learning rate. This is the main step in this algorithm. So now let us try to understand the gradient descent algorithm. Suppose this is our solution surface, where on x-axis we have weight and on the y-axis we have the criteria function. Okay, so here we have considered that our initial weight is J1. So suppose this is our initial value, and here we have a rolling ball. So if we leave this ball, then it will move in this direction. So we have to check that whether this equation is moving in this direction or not. At this position, we can compute the gradient. So gradient is nothing but the del y by del x. Okay, so if you see here, then here the gradient is basically the positive. Okay, so when we will update the weight vector, so eta k into gradient of j a k, and this value is positive for this location. Okay, then what will happen? The total term will be subtracted to the first initial weight. So the next iteration weight will be reduced. So that means the next iteration the weight will move in this direction. Okay, so it will try to approach to the global minima. Okay, but somehow if our choice is here, if our initial weight choice is somewhere here, then maybe our initial weight will be here. Okay, so in this case again we will compute the negative gradient. So at this point our negative gradient is so del y by del x, and at this time, and when you will compute the gradient, it will come the negative gradient. Okay, so when we will consider at this position, then this term will become positive, and that means in the next iteration weight will increase, so that our updated weight will move in this direction. Okay, so our solution vector will oscillate in this curve, and when it will settle down, it will come to the global minimum, and here we will get our solution vector. Okay, so that means iteratively it will come to the solution. Here eta plays a very important role to update the weight. So basically eta defines that how fast the weights are updating in consecutive iterations. So if eta will be very small, then update in A will be very small, because this is a factor which is multiplied with the negative gradient. So if the eta will be small, then there will be a small change in the weight. So it will go very slowly towards the negative gradient. If it is this side, it will move very slowly, but towards the negative gradient of the criteria function. Okay, if eta will be very large, then it may be possible that our solution vector will go out of this curve. How? Just consider that if we are here initial weight and eta value is very large, then this value will be large and it will give a very strong force to this ball. If we consider this as a ball, then it will give a very strong force. Then it will may go out of the curve. So here it totally depends on the value of eta, that how fast this weight vector is updating. So if it will be very slow, then it will update very slow. That means it will take many number of iterations. And if it will be very high, then maybe we will not converge to our solution. So there should be an optimal choice of this learning parameter, so that we can get towards our global minimum and we will get the optimal solution of this weight vector. However, we can define this learning rate in terms of Hessian matrix and the criteria function as where H is Hessian matrix at AK. Okay, and how it is defined? Hessian matrix of F is the mapping from D-dimensional space to R is defined as the Jacobian of del F. So if F is given some function, we have to understand what is the Jacobian of the grad F. The Hessian matrix of X can be defined as del F by del x1 del F divided by del x1 del xd okay, where the Jacobian matrix is defined as okay. So how this Jacobian matrix is defined? Okay, so this is the one way we can define the learning parameter, but usually we consider a constant learning rate. Okay, we choose the constant learning rate, and usually we choose a small enough so that our learning process will be good, our accuracy will be good, and in the less number of iteration it will learn and it will approach to the global minimum. Okay, so here there is no very general answer how to set the learning rate optimally. The best solution depends on the application, so the value depends on the application. So this much for this lecture. So I hope I am clear to you. If you have any doubt, you can ask in the comment section. Thank you.